Yeah, hello everybody. In the last class, we saw how important a VLSI architecture is in the VLSI design flow. So, depending on the user requirement and the overall VLSI design requirement, a proper architecture requires to be selected. So, there is no one particular architecture which is the best. So, it depends on the kind of requirement. So, you need to select. Now, you go to optimize the total requirement. A particular architecture has to be chosen for a specific application, right? So today we'll just see some of the microprocessor architectures which are already available in the market. Right. So let's first define what a microprocessor is. General purpose microprocessors are also known as a CPU for computers, that is the central processing unit for computers. Okay. So a microprocessor or a CPU does not have a RAM, ROM, input, output in the chip itself, right? So if you see here, this is a motherboard, and CPU is only the processor which is placed over here. So you find that and this motherboard that houses the RAM, ROM, input, output, timers, right, and the communication ports and all. So you see the CPU is dedicatedly used for the it will have a control unit, and then it will have an algorithmic logic unit. So ALU and control unit together forms an CPU which does the processing. These are all peripheral ICs which are required external to the CPU, which is put on the motherboard. Okay, so here it's written Intel 8086 or Motorola 680, but today's even i7 processor, i9, i11 processors, they are all like this. It is you have an external motherboard onto which the CPU is mounted, and you have all the RAM, ROM, port, timers and all mounted on the motherboard, and not it is not integrated along with the CPU chip. Okay, so this is how a microprocessor looks like, right? So inside the microprocessor we have an arithmetic logic unit which does all the computations, right? Now there can be several types of architectures. We'll see that, wherein the arithmetic logic unit, two inputs needs to be given to an arithmetic logic unit, and there will be one output. So each, like, either you can have inputs from two registers itself, or you could have an input coming from one of the inputs coming from the register, and one of the inputs coming from the memory. Generally two inputs from the memory is not allowed. So in certain classes of microprocessors you can have both the two inputs only from a register. We'll see those classifications later on. Or in certain other classes of arithmetic logic units, you have one input coming from the register. Register is internal to the CPU, and one input coming from the memory. Memory is outside the CPU. That means from the RAM or the ROM. Okay, so that generally it's the RAM. ROM is used for BIOS programming, the storing the BIOS programs, right? So this is how generally an ALU works within an CPU, right? And it requires a few internal registers. So now also the output of the ALU, it depends on architecture to architecture. In most cases the output will be one of the inputs only. So once you do A plus B, the result will be stored in AL itself. So that is why it is known as accumulator. In some other architectures of microprocessor, you do A plus C B, result will be stored in a third register. It could be C or something like that. So those kind of things we are going to see today, and obviously there will be some flags, that is on the result of the to doing an arithmetical or logical operation. Certain flags will have certain conditional bits, like if there is a carry or there is a sign, or if everything the net result is 0. So one flag is a big register, and each bit corresponds to some particular status on completion of the operation of the ALU. Okay, say after addition subtraction, if there is a carry, the carry flag will be set, and if the net result is 0, the 0 flag will be set. So depending on microprocessor to microprocessor, the number of flag bits also will change, and each of the bits corresponds to certain status that also can change. Okay, then you have certain bus interface units, and you have certain registers here, and one of the most important is instruction pointer. So it is just a kind of counter. So as we keep executing the program, this will automatically, the content will increase, indicating where is the next program to be fetched from in the memory. So when we write a program, the entire program is stored in the external memory, right? So like suppose I write a program in my hard disk. So during execution, the important if I go back here, from the secondary memory, from the hard disk, the program which needs to be executed presently will be fetched and placed in the RAM here, right? So from the RAM, right, and then this generates the address of that RAM. So instruction pointer will point to where is the next line of the program lies in the RAM. So it will keep fetching the program from the RAM. Okay. Also you have, when the ALU is doing certain computation, right? So what the control, to save time, this is also known as a kind of pipelining. To save time, the next instructions are brought, and it is prefetched and kept here, and it is also decoded. Okay, we'll see what is why is there is a requirement of decoded also in today decoder also. Why is that the instruction requires to be decoded? Because the instructions could be complex instructions, right? It is not a simple instructions. So in most of the just to simplify the program, we permit complex instructions also, but the CPU may not be able to execute those complex instructions in one go. So there is a requirement of decoder also. So this is how a microprocessor architecture looks like. Okay, is it okay with all of you? Okay, you have an ALU, right, and in which you can have two or more datas. Generally one of the data has to be from an internal register, the other one could be from a memory or from a register. So you have certain registers. The output of the once the ALU does the computation, the output of the ALU could be one of the input registers itself, or it could be a third register. So both will has its own scheme has got its own advantages and disadvantages. We'll see that. Then there will be some flags. The flags are essentially to indicate the status after the ALU operation, whether there is a carry, there is an if it is a positive number, it's a negative number, or right, if there is an overflow. So all these conditions will be detected by the flags. Okay, that will be indicated by the flags, and you can read that flags and decide accordingly what should be the next step, right? You have an control unit. The basic purpose of the control unit is to fetch the instructions from the memory, queue it up, and while the ALU is doing the computation, it will decode these instructions so that the next instruction for the ALU is ready. So the instructions which is being fed may not be direct. We may not be able to give it directly to the APU. There might be a requirement to decode that instruction. So that function is done by the control unit. So these are the registers which are used by the ALU for storage of data and for computing, and these are there will be some registers which are used by the control unit also, right? Okay, so this is then a general architecture of an 8086 microprocessor. So other processors also will have something very similar. right? And what is the difference between a microprocessor and microcontroller? So one of in short, I can say a microprocessor, okay, is not only a CPU, but within a this is the CPU, which is a microprocessor, and in a microcontroller within a chip you have a ROM, you have a RAM, input, output, and interface devices. You have timers, counters, analog interfaces, output, everything is put together. So you find this is the chip and Arduino chip, and on the board there is hardly anything, right? Only some ports are available where you can give, and then there is some regulator, power supply regulator, where you can switch in the plug in the power supply. There will be some input ports and an output. So everything is put within this chip. Okay, obviously because of space constraints and the requirements of microcontrollers generally we use for small computations and small tasks, less complex tasks, and hence the CPUs are not that very high level one, or you could say it can't do very complex instructions, or it will take a large time to do complex instructions, right? So the CPU is not very efficient. Okay, so it is a scaled down version of the CPU as far as the functionality is concerned. Okay, but then all these things are, so there is no requirement of a big motherboard like this. So it does small functions, but everything is integrated within a single chip. So that is microcontrollers. Okay. So microprocessor types, it can be classified into 8-bit, 16-bit, 32 and 64-bit processors. As on date, most of the processors which are coming in the market are 64-bit processors. They are all back compatible, means the programs which has been written for 32-bit processor can be run on a 16-bit, 64-bit processor, but it's not true other way around. The programs which have been specifically written for 64-bit processor cannot be run on a 32-bit processor. Okay, so it is known as backward compatibility. That means and 16-bit program can run in 32-bit processor or a 64-bit processor, right? But the other way around it is not possible. Right. Microprocessors can also be classified based on the instruction set structure. Okay, so reduced instruction set computer it could be, or complex instruction set computer. We are going to see these two things in detail in the next few slides. So I leave it here for the time being, and based on the functions also we can classify the microprocessor. There could be a general purpose microprocessor, which is generally what is there in our CPUs and all. There could be some special purpose like image processing ICs. They are targeted towards image processing, or floating point and calculation processors and all things like that. So depending on the functions also you could classify microprocessors. Okay. Now the microprocessors, one very important thing which links the software and the hardware is known as instruction set architecture. So there is two ways of looking at it. First, the hardware, if it is fixed, right, once a microprocessor has been designed, right, for an user, say set of instructions is given by the hardware engineer, so that the software engineer accordingly can use the ISA architecture to write the programs, right. If you write very high level applications, the microprocessor will not be able to decode what it is. So you have something known as ISA, which forms the interface between the hardware and the software. So say for example, once 8086 is made, so there are certain ISAs which are specific to 8086, right. So you have certain kind of operations which are permitted in 8086, like you can add data of an memory and an register. You can add data from a register to register. You cannot add data of a memory and memory. So so you have an instruction sets which has been given by the hardware engineer, because he has already implemented the hardware inside the CPU. So a set of instructions has been given. Now the software engineer has to stick to that set of instructions which is available to him. Okay, so that becomes the guideline for the software engineer. So I have a set of ISAs. Okay, ISA stands for instruction set architecture. So here the ISA has come as a result of the CPU which has already been designed. Okay, so that is one way of looking at it. Okay, so they could be other way also, like I start from a top down approach in which I decide, okay, this is the architecture which I require for my specific purpose, and then accordingly I write an ISA, and based on that ISA a hardware is made. Okay, now here the requirement is specified by the software engineer, and he makes the ISA, and hardware engineer accordingly implements these in hardware which can execute the ISA. Okay, so because if you see here all the standard cells like AND, NAND gates, those should be that will be available in the VLSI library, and based on the ISA, okay, how those will be integrated to form a CPU. Okay, so you can have this kind of so you decide the architecture, and then you write a program and convert it into ISA, and the hardware engineer based on the ISA he will make the hardware. Okay, so otherwise initially itself the CPU is made based on certain requirements, and then the ISA accordingly gets restricted based on the CPU design, and the software engineer uses those ISAs to allow to compile the software. So this is a two-way. So ISA has got serves both the purpose. Okay, so that is how it is. Now the instruction set, this is what we discussed, is summarized here. The ISA acts as an interface between the hardware and the software, specifying what the processor is capable of doing, as well as how it gets done. Okay, so this is the programmer's manual. Okay, because everything the machine can do has been clearly laid out in the ISA. So he has to use one of these instructions only to write a program finally, right? So the ISA defines what are the data types, right? Registers, how many, what all, how the memory can be interfaced with the registers, and all those features. Everything will be available in the set of instructions which is available to the software engineer. Okay, so this is set of instructions. So now here in an instruction set architecture can also be classified in the number of operands which are used. Okay, for example, suppose this is an 3 operand instruction set where A is equal to B plus C. Okay, so obviously if this kind of ISA or instruction set is permitted, then the processors will be different. So what is the difference? If you see here, I am adding B and C, and the net result is available in a third register. So A plus A equal to B plus C. So this is known as a 3 operand ISA. Right. So some of the processors, these are the like ARM and AVR32 and Power ISA and all, they use these kind of architectures. Okay, so the hardware accordingly will be different, since this kind of instruction is permitted. So the actual hardware will be different out here, right? There are certain 2 operand architectures also, where you can only write A equal to A plus B. That means when the result will be stored in the here you have destination, this is the source, and again the result will be in the destination. So this A will get modified with the, here you don't lose data out here, right? B and C you are adding, and the result will be in A. So your inputs A and B, B and C will remain as it is. In this particular case, you do A plus B. Then one of the thing which you are adding will be initially will be A, but subsequently that A will be updated with the sum, so that initial data gets lost. Okay, so this is known as two operand architecture. But most of the, like, these are the kind of instructions. And if for example, if I have to do right A plus B plus C, right, if I have to do A plus B plus C, then I will require two instructions. First I write an A plus B, and then write again A plus C, because now A has got A plus B. Okay, so the single instruction needs to be split into small instructions in this case. Okay, and most of the Intel processors, they use two operand architecture, like starting from 8086 and even today's processors, most of them they used a two operand architecture, because it has got some unique advantages which we will see shortly. So 2 or 3, so the choice is, you need to make a choice based on your requirement. Okay, so when we design an VLSI system, how will the architecture be? 2 operand one or a 3 operand one? In the 2, there will be a source and result. In 3, there will be source 1, source 2 and result, right? Here the destination is the result. So you do an operation between the source and the destination register, and the final result will be stored in the destination itself, right? So obviously there will be some trade-off. Here you will find that the instructions are very short, right? So you can write like Z is equal to X plus Y, right? So whereas in a 2 operand instruction, this may not be possible directly, so you will have to use 2 instructions instead of one instruction. So in a 3 instruction architecture, the number of instructions and the program will be smaller, but hardware implementation wise it is going to be slightly more complex. So that is the trade-off, right? If you have, like for all the Intel series, you just have a source and result, so this implementation in the hardware is very simple, but it will result into a larger program. Okay, you will have to write maybe to accomplish some task, you might have to write a larger number of lines of programs. Okay, so that is the trade-off which you will have to do. Okay, so now let's take one example. Suppose I have to add, okay, all data which is available from in the memory from say memory location 2002 and 2010, right? In a source and result one, what I can do is, you have done 8086, right? So you have some basics of how this data transfer instructions and all look like, right? So suppose I have to add all data which is there starting from 2000 to 2010. So I put the data which is available in 2000 into A, and data which is available in 2001 into B, and do an add operation, right? So the result will be in A. Then I just increase the say B, I can put the pointer which is corresponding to 2000 in say D or something, and then increase the counter and fetch the next data into B and add. Okay, so the net result obviously will keep getting updated in A. So I get in the next cycle I get the next data into B, add, next data into B, add. So when I am doing a simple addition of 10 adjacent memory location data, or so since you are putting this data back into A, you keep updating the contents of register B with a new data and keep adding it. So finally the net result will be available in A. Like whereas if you have this kind of instructions, this kind of architecture, so you get one data into A, one data into B, you add it, you will get the result in C. Then you put the C right into A, and you get the next data into B, and then add it. So an additional transfer instruction from C to A will be required. So you see, this is although this instruction wise it appears that the two source and result is an much it has got an is a less powerful tool, but then you will find for many applications this simplifies the entire operation. Is it understood? Yeah, Damodaran, have you followed what is the advantage in this system, right? For example, if I have to add 10 datas from the memory, sequentially they are stored. Initially I get the data of the first memory into A register, and the second data from the memory into B, right? I do an add operation, and then I go to the next memory location, get that data into B, and I do add. So I am doing a sum of all the 10 numbers. So I keep doing add. So the moment I do the add operation, obviously in A, in the same register, the data will keep getting updated, right? So if I have to do the same thing, which an 3 instruction 3 operand architecture, in this case I get a data from the memory 1 into A, this from the second memory into B. I do an addition, I will get it into the C. Now what about, now where do I get the third data? I can get it into B, right? And what is the result of the first sum operation that is available in C? So I need to get that C into A. So you see here, so there is a problem out here, right? So there is it is not that three. So this will have certain other advantages. Okay, many times we will see that also shortly, right? Okay. Now when we talk about a microprocessor architecture, there is also two different, they can be classified into two different manners in which the data is stored into the memory and retrieved back and also computed. Okay, they are known as the Big-Endian and the Little-Endian, right? So if you see here in the big, if this is an 32-bit data, right? Okay, so these two is the first byte, this is the second byte, third byte, and fourth byte. This is the LSB byte. So if you when I store into the memory, if the low, like suppose for example a memory A corresponds to 2000, 2001, 2002, 2003. So in the lowest memory, that is 2000, if I store the MSB, right, and in the next memory 2001 the next significant byte, and 2002 the next significant byte, and the least significant byte if you are going to put it in the highest memory. Okay, so 4, like it is an 4 byte data. So 4 bytes are being used, and the highest memory location you are putting the LSB, and the lowest memory location you are putting the MSB. So this is known as Big-Endian, and in Little-Endian it is exactly the opposite. So here you will find in the lowest memory byte you are putting the LSB, right? So it starts in the reverse order, and in the highest memory by location you are putting the MSB here. So most of the processors, whether it or modern day processors, they use the Little-Endian. Okay, so there are certain advantages of using Little-Endian. So only in networking requirements the Big-Endianness is used, right? So if you see the advantages of Little-Endian is, for example, say certain operations, and I am writing 16-bit data into the address. a 64-bit value into the memory address, like 0013, right. So the 13 will be written first, and then it is only 0013, right. Okay, it's only an 2-byte information. Whereas the memory, for some purpose, because I am sequentially generating lot of data, so I have earmarked 64-bit for each of the data. So I will find 1300 being stored here, and then rest all are stored as 0. So when I am doing a read operation, right, if I am going to read from the memory, and then I realize that it is only an 8-bit data or a 16-bit data. So I can go back to that memory and just read 8 bits, and since the LSB is stored, I will be able to get back this data, right. But in the if I store 00s here, and then if I store the LSB out here, then I can't go to that memory location and just read the 8 bits, because here instead of the LSB, MSB has come here, and they could be zeros. The actual data could be residing in in other memories. So if you, in the Little-Endian, it becomes an easy in first of all, once the data is stored here, so it starts from the LSB. So if you later on realize that the MSBs are all zeros, so in the read operation you can just pick up the from the starting point of the address, you can pick up the required number of bytes. Okay, so that is one advantage, and it is easy to convert from an 16-bit to 18-bit and things like that, because the MSBs are all zero. So these are some of the advantages of the Little-Endian. That's why it is being used vastly in the processors. Okay. Now this is what we need to understand very clearly. What is an CISC and a RISC? Okay, CISC stands for complex instruction set computers. So the microprocessors can be classified into CISC and RISC, whereas RISC stands for reduced instruction set computer. Okay, so these are two type of architectures of the microprocessor. Instruction set means, obviously, since the architecture is complex, and the instruction is complex out here, so the architecture will be different. Here the instructions are reduced and simple, and so the architecture out here for these kind of CPUs will be different. What is an CISC processor? It is a general name for CPUs that have a complex instruction sets. So most of the Intel families, what we have 8086 and higher ones, and Motorola 86 series, they are all based on CISC architecture. Okay, so the advantage of CISC is, each instruction can be complex, right? So a small amount of memory, it requires small amount of memory, small cache memory. This also will see what a cache memory is. So the total memory requirement to store a program will be much lesser in a CISC. Right, like complex instructions. For example, I can write an move, right, into A. That means in 8086 you might have learned, right, and move into A, and then you can write BP plus 100. So what it is going to do? Within square bracket. So where will the data be written? It will be written into AX, and from where? So that address will be specified by the contents of an BP register plus the offset it is there. So you see how complex you can write an instruction where it will compute from where the address data requires to be brought. Okay, so first it will go to the you are writing move A within square bracket BP plus 100. Okay, so it will first go to the BP register, see what is the contents in the BP register, add another 100 to it, and then and whatever is the result from that memory location, you are going to get the data. So that is what it is known as CISC, right? So it can handle complex instructions. So now when you write a program, so since it is so flexible, you can write in a single line, you can write this such complex instructions. So the total space required to write an program is much lesser, but so that is what the advantage of an CISC architecture is all about, right? Okay. So but the disadvantage is, since these instructions are and the CPU is also now complex, right? Because you have to implement these complex instructions, so obviously the CPU also becomes little bit complex. So pipelining and all is slightly difficult out here, right? So in the reduced set of instructions, right, you can't have such complex instructions, and then the length of the instructions will be fixed. It is only a single small instruction you can write. Okay. So whereas here some instructions like increase a, that is on a single byte instruction, whereas move, what we discussed, it could be an 5-bit 6-bit instruction. So the length of the instruction is also different in an CISC processor, whereas here the length of the instruction is fixed. There will be single line instructions. Okay. It could be 8-bit or 16-bit, it will be fixed. Okay. So within one clock cycle the instruction will be fetched, and then you will do the operation. So when you write a program, since you can write only simple instructions, so the program will become very lengthy. So that flexibility is not available for the software engineer. He has to write big programs now, but the hardware implementation is very easy in this particular case, right? So that is what an advantage of RISC is here. So the program becomes lengthier, but then the hardware becomes pretty simple here. We will see little more details into it, like the semantic gap. That means from an high level language to an CISC architecture, the gap is very low, because you can write complex instructions also in CISC, whereas in RISC the gap between an high level language and RISC is very large, because it can support only very simple instructions. So you have to put in lot of thought process to write an RISC. Okay. The code size is very small out here, because complex instructions it can have. Here you will find it is very large. Okay. The code size, but RAMs are cheap, so you can if you have a huge RAM, then that doesn't become an issue. The cost is high, the cost is low, because it is high because this complex instructions, actually if you see here, once you write the complex instructions, these complex instructions will be let me go back here, will be brought by the control unit. Okay. And it will have to be decoded first. So you will have a decoder hardware also here, because you are writing very complex instructions, they need to be decoded. Okay. Sometimes the address also needs to be decoded, right? So the code will not directly indicate from where the next data requires to be given to the ALU. That particular address itself might be so complex that you might require a decoder to decode that particular address. So you will have a decoder. So the hardware requirement goes up. Okay. So that is what is written here. Okay. Right. So the hardware requirement is low here, and it is the here it is high. So accordingly the cost also will vary. It is fast only if the compiler generates the opcode, appropriate opcode. That means once you have an CISC program written, so the compiler has to generate an appropriate code. Here it is slower, because there are many lines in the program, but then pipelining can be used in this very easily in the RISC processors. So overall this can work fast. In fact, in our mobiles and all, since we use an RISC processors, whereas in the CPUs we use an CISC processor. In the mobiles and all, the mobile processor is not expected to do very complex programs, simple programs only, right? So in that case, you have an RISC processors, like, right, small portable devices, where whereas the computers, they are supposed to do where we write very complex programs. So that is why the places where we use CISC. So in our say mobiles and smart watches and things like that, we generally have an RISC processor, whereas in our CPUs and laptops you have the CISC processors, okay, because the CPUs and laptops, they do high-end computation, so you have an you can have a complex set of instructions, okay. Whereas here the application itself is limited, so we can use an RISC pipelined RISC architecture, right. Now let's discuss it little more. Now if you see here, the CISC processor, these are the for 8086, okay, 8086 is also CISC processor. So you see the addressing modes, okay, move AB, move AX BX, okay. What will it do? The contents of BX is moved into AX, okay. So this is one kind of instruction. It requires say 3 bytes, okay. Now you can also do move CX, and you can give this data hexadecimal. This is second kind of instruction, wherein one set of data is specified in the instruction itself. So now this data is being moved. So now the total instruction requires to be, when we are storing this particular instruction in the memory, it will require slightly larger space. So this is okay, but both might require the same amount of clock for execution. Now coming to the third one, if you see here, move AX 1 2 3 4 within square bracket. What does it mean? We have to first find out what is the contents in the memory location whose address is whose offset address is given by 1 2 3 4, right. This is just the offset address. So along with this offset address, if you have seen in 8086, the physical address is calculated with the data which is there in the DS register, right. You have some DS register out here, right, then the physical address is generated. So once you give this these kind of commands, now the physical address will be generated, and then so you see once you write this instruction within the CISC processor, a micro program is running, right. This data will be fetched, and a decoder will run a micro program to decode this instruction and find out what is the physical address, right. So it becomes complex, right. Now if you see register indirect addressing, here we want to move the data of the CL register, okay, into some memory location whose offset is stored in BX register. Now this becomes even more complex, right. So now there are instructions in which you can write move BX plus 100 within square bracket CL. In that case, what happens is the data which is available in CX is stored into some memory, and what is the physical address of the memory? The offset is given by the contents which are available in BX plus 100, and then again you will have to refer to DS to generate the physical address. So you see here how complex instructions it can handle, but within a single line, it is like this line itself, although it appears a single line, it is a micro code in itself, right. And this is what exactly the decoder in the CIS and the control unit does, okay. It runs a small micro code within itself to decode these instructions. So a decoder is required here, right. So all these Intels like Motorola 86020 is a 30-bit CISC processor. There are 18 instruction modes, and there are total more than 600 instructions, okay. Some instruction is just one word, right, and that is 16 bits, and some instructions are 11 words, okay, in length. So you find, see how much flexibility is available here, okay. So this becomes a very handy tool it makes the life of an software engineer pretty simple, because it can handle okay, but the hardware implementation is that much difficult. Whereas in the RISC processor, like Berkeley RISC-1 has just got 31 instructions, okay, and the Stanford MIMS has got just 60 total instructions, and IBM 80 has close to only 100 instructions. So they are all only single word instructions, but then the software engineer has to accordingly write a lengthy program to execute a certain task. So that is the basic difference between an CISC and RISC. Okay. Now, if you CISC this architecture we already saw, since you have done 8086, and so this is the kind of architecture which is there, right? This is an CISC processor. You have already done 8086 in your last semester. So let's concentrate on how an RISC processor looks like. So you have an ALU, right? In ALU, in an RISC processor, you can only add or do any operation between register and register, or register and immediate. Okay, that means within the instruction, if I go only these two, the first two instruction types are permitted in RISC, either between two registers operation, or register and then a data which is specified in the instruction itself, right? Between memory and register, those kind of things are not permitted here. So you will have two mux here. So from the instruction set, and I can either through these mux I can select two registers for an ALU operation, or one register and one data which is available in the instruction itself. So the ALU can do only that kind of instructions. Okay, and the result will again come back to the register file here. But you will find one wire from here. It is also coming to the memory. It is because that sometimes in certain instructions ALU can generate the address of the memory, and then again data will be transferred from the register. So from the memory, data can only be brought to the register. Okay, from the register data can go into memory. From the memory to the ALU, it can't be done. So everything is through a register in between. So the instructions are very simple. There will be large number of registers, and you can do any kind of operations between a register and between any two registers. So that makes life pretty simple. You can only then subsequently you have to write one more instruction to to fetch the data from the memory to the register, or to take the data from the register to the memory. So the instructions are small instructions. They are all single word instructions. So that is the advantage of having an RISC processor, right? Like for example, suppose I have to subtract A and B and put the data result into A. That is my within square A means it's a memory location. Okay, not the registers. Okay, for registers we will use the nomenclature R. When I write AB, it means some memory location in the RAM. Okay, so I have to add data available into RAM memory and put the result in into the memory location. So in a CISC code, this is particular one CISC code in which a memory to memory operation is also permit. So you can straight away write and subtract like this. So you are subtracting the data and putting the data here, and in B whatever data is available, you are adding one and updating the data in the B. So this is what is. So in CISC you just write two instructions. Whereas if I have to do the same thing in an RISC code, first whatever is available, data available in the memory location, I get into R1 register. Whatever is available in B, I get into the R2 register. So this R1, R2, R3, R4, if I go back here, they are all these registers. Okay, A1, A, B, C, D, what we are speaking, they are the memory locations here. So now RISC processor can do only ALU operations from the register. So I am getting the data from A into R1, from B into R2, then I am adding R1, R2, and the data gets stored into R3, and then B I need to increment it by 1. So I am adding R2 and 1, putting it to R4, and then I am using this store command. So in RISC I have a store command wherein the data is stored from the registers to the memory location. I will have a load command from where. So I have one store command to get data, to write data into the memory, and load command to get the data from the memory to the register. So you find this is what we did: load word, store word. Okay, so this is the two commands which. Now if you see here, instead of 2 lines, 1, 2, 3, 4, 5, 6 lines of program is required here. So the program becomes lengthy in this particular case, right? So now you can the advantage of RISC processor is you can do pipelining, because they are all simple operations. You will find that you can insert a register. So in the very first class we talked about pipelining, right? So that kind of pipelining can be done easily here, because they are all small instructions, and if you see between the ALU and the register file, and you can have a pipelining register here, pipelining register here. So the overall speed of the system will become faster. So you can do that, right? Okay. Now coming towards the end of this session, we also have something known as the cache memory. Okay, what it does is the main program is written in your hardware, like secondary memory. It could be your hard disk, which is there, or a pen drive, or whatever it is. Whenever a program is being run, so the relevant information from these secondary devices is brought into an DRAM. Okay, DRAM is for dynamic RAM, and now the program resides in this DRAM and you are running it. But certain portions of the program will be referred to constantly. Okay, every now and then you will keep referring to those particular lines of the program or certain data in the programs. So these are slightly slower. So within the CPU you can have a cache memory. Okay, these are DRAMs, these will be SRAMs. Okay, because SRAMs are much faster than DRAMs. Okay, so but then why do we use DRAMs outside is because DRAMs require much smaller space and power. And then so you can have larger DRAMs, because these days initially if you see here you could use 1 GB RAMs was good enough, but presently even 16 GB RAM, some of the processors and some of your programs require 16 GB RAMs also. So for high packing density you generally have DRAMs, dynamic RAMs out here, right? Whereas the SRAMs they occupy more space, but they are very fast, because you have a cross couple latch in SRAMs, right? You might have learnt in your VLSI classes. So you have these SRAMs embedded within the chip itself, within the CPU. Cache memory, not a huge memory, small memory, but some portion of the main memory which is used over and again, is always put into that, so that now the data transfer between the CPU and this cache RAM, okay, is very fast, and so the overall performance of the CPU is improved. Okay, then you have something known as an secondary cache, in which you can have an additional SRAM placed outside the chip also. From the main RAM, then some portion of the memory is brought into this SRAM, and from here it is taken to the CPU. So this is known as the L1 cache and L2 cache, right? So in big servers, so these kind of things are done, where you have an L2 cache separately SRAM over and above the DRAM, intermediate to the DRAM and the processor. You have an L2 level 2 cache SRAMs also. Okay, so this normally not there in our not normal CPUs, but in big servers and all, you have this system. In our CPUs, the cache memory is within the CPU what we have for home applications. Okay. So this is all about the RISC computers. Okay. So so thanks a lot for